Okay, come. Hello, good evening. Welcome to the next live session. Uh, we missed last week because of public holiday. So, what we did in the last 2 weeks was a lot of work. We learned about we had stopped at the point where we found what is the modulation depth of modulation bandwidth of LEDs. We moved on, learned how a resonator works, and we also talked about the gain medium itself. We talked about how the laser rate equations are written. We also talked about how you can get a larger modulation bandwidth from laser. Then we talked about how to make use of the laser, in the sense understand the limitations of the laser. We talked about the intensity noise. We talked about the phase noise from the laser. Then we moved on to understanding external modulation in case you have reached the content of week 4. So I would request you to start the questions right away. And as usual, please ask the questions corresponding to the contents in week 3 and week 4. Or even week 2 for that matter. Please type your questions in the chat window and I can start answering those. I will be here to answer only your questions. So unless you ask me a question, I will not be able to respond. So I have a question from Arjun. How is PAM4 electrical signal generated? Wouldn't the adding electric field cause interference? So let's just check what is PAM4. So you have 4 levels, and let's say you call this as 0, 0, 0, 1, 1, 1, and 1, 0. Okay, just by some way of calling these levels. Now, how do you generate this? So you saw that if you take a Mach-Zehnder modulator, right, and let's say you are taking a dual drive modulator, right? So you have an electrode in the middle and then you have an electrode here. You send your light in, it splits, and then it combines. And in a dual drive modulator, we said that we're going to give a voltage only half that is required for a single drive modulator. But in any case, what we found is that if we send light CW input, what comes out is the modulated output, right? And the signal that you have to modulate is given in the RF port of the modulator. Now, if you look at the transfer function of the modulator, which is your output intensity versus voltage that you apply here. Let's say that 0 volt corresponds to completely constructive interference. That need not be the case. There is an assignment problem where you will see that 0 volt need not correspond to complete constructive interference. There could be some residual phase difference between the arms. So, but let's say it's all an ideal modulator. The intensity transfer function is going to look like this. Okay, the transfer function is going to look like this, where this is 0 volt, and if you apply a phase difference, right, a phase difference of pi between the two arms of the Mach-Zehnder interferometer, you're getting a null, and that corresponds to 0 intensity. Now, how do you do the modulation? You say that you will, let's take OK. How do you do OK modulation? What you do is you apply, let's say you want to modulate this on-off keyed signal, this on-off keyed signal, right? So a level 0 and a level 1. Now, if you want to get the largest depth of modulation, what you should do is you first find out what is the V pi of your modulator, right? So let's say that V pi is 5 volt. Then what you do is you bias the modulator somewhere. Let's say if this V pi is 5 volt and this is 0 volt, you bias it at midpoint, 2.5 volt. And you give a level 0, and instead of 1, you give 5 volt. This is how you would apply your input. Corresponding to that, you will now see how the output, let's see how the output looks like. So you will see corresponding to level 0, you will have a high, and corresponding to level 1, you will have a low. So you get something like high and low like this. Of course, it's inverted, but in a digital system, inversion does not matter, right? You can also get it non-inverted if you bias it at this point rather than at this point. You know, if you bias it at point B rather than at point A, you will get it non-inverted. So this is how you generate your on-off keyed signal. Now, if you want to generate PAM4, what do you have to do? Instead of these two levels, so this is low intensity corresponding to 0 state, and this is high intensity corresponding to 1 state. Now, if you want to get a PAM4, you want to get 4 levels instead of 2 levels. All what you need to do is to actually do this. Take the transfer function of the modulator. Imagine that you have, this is your intensity, this is your voltage. It's called transfer function because it's a transfer from voltage to, this is not current, this is intensity, optical intensity, from voltage to optical intensity. That's why it's called transfer curve. Now, let's say this is the transfer curve. It follows cos square phi. That's what we derived in the class, right? So if you want to now start requiring 4 levels, let's say we bias at this point so that there is no inversion, and these are the 4 levels, right? So this is my level 1, this is my level 2, this is my level 3, this is my level 4. And let's say this is the voltage. This is how the PAM4 signal is looking like. So this is voltage axis, and what I'm drawing here is actually the time axis. As time progresses, the output level goes between level 1, level 2, level 3, level 4, and let's say it is going back to this. This may represent, as we said earlier, 0, 0, 0, 1, 1, 0, 1, 1. What would be the corresponding output levels now? So corresponding to 1, this level 1 or level that I've marked as 1, you will get 0 output. Corresponding to this 2, you will get, corresponding to this voltage change, I will get this. Corresponding to 3, I'm going to get something like, so it's remaining at 2, this is 3, and corresponding here, I have this, and this goes on, right? So there's no question of interference, because at a given instant of time, you're giving only one voltage. In this case, you gave, I decided to choose my bias point here in the rising edge of this transfer curve so that there is no inversion. So there's no interference because at a given instant of time, you are giving only one voltage. The other interesting consequence here, if you notice, is that even though the levels here are equally spaced, this spacing is the same. Let's say this spacing, this voltage spacing, let's say it's all delta V. At the output, you see, even when you are drawing the schematic, you found that the output is unequally spaced. And why is that happening? The output is going to be unequally spaced simply because of the fact that this transfer curve is a nonlinear curve. So this intensity difference could be I1, here it could be I2, here it could be I3. So the slight subtlety here is that even though in PAM4 you can give 4 levels at the input and you get 4 output intensity levels, if you do not do something, if you do not do a pre-compensation, the output intensity levels, the optical intensity levels are going to be unequally spaced. And that's not something you don't want in a communication system. You want the levels to be equally spaced. So how do you do that? The answer is very simple. You know this transfer curve, you know the form for this transfer curve. This is cos square pi v by v pi. Right? Now you find out if you want your, so when v is equal to v pi, this became cos square pi, and that is why you got a 0 here. And when v became 2v pi, right, this became pi by 2, this became 2 pi, and so you got a level of high level here, right? So if I say my I out is equal to I in times cos square pi v by 2 v pi, if this is my input-output relation, or the transfer function is I out by I in is equal to cos square pi v by 2 v pi. I know this, and I know that ideally this answer, as your v changes from v1 to v2 to v3 to v4, which is corresponding to here, v1, v2, let's say this is v3 and this is v4, you want your if you want your outputs to be equally spaced, what you simply need to do is to make these levels unequal, right? So you can pre-compensate. You can calculate what values of V will now give me my cos square answer has equally distributed between 0 and 1, right? So you can say that what should be my cos square pi V1 by V pi so that my answer is 0. What should be my cos square pi V2 by V pi so that my answer is the second level you want it to be, how much do you want it to be? You want 0 and 1 to be equal to, so this should be 1 by 3, this is 2 by 3, and that should be 1. So you can demand that cos square pi V2 by V pi must be equal to 1 by 3. You can calculate what is V2, which will give me that answer. So the trick here is to give unequal voltages at the input so that you can compensate for the nonlinear response of the modulator. Now, this is true not just for PAM4, any multiple amplitude modulation levels. Later on, you will see in 16 QAM, which is PAM4 and 4 levels of phase. There also, you need to do this kind of balancing to compensate for the nonlinear response of the modulator. Okay. The other option, of course, is to actually say that, okay, how do you get rid of nonlinear response? There is one more method to do this. That's a very slightly inefficient method. What you can also demand is that I do not now use the entire range of the modulator. Let's say I use only this range of the modulator, which is in that range where it is more or less linear, right? So if I pick only the linear range of the modulator and then confine my voltages, my 4 levels to be within this, then also I can get output which are equally spaced. But this is a bad solution because you are not using the full extinction of the modulator. So if you were to use a full extinction of the modulator, so that the levels that you're seeing are extremely different from each other, and also at the same time the difference in levels are equal, you have to do this equalization. I hope so that answers your question. There is no interference happening simply because at a given, you can imagine that it is just like OK, but at a given point, there's only one voltage. So you will get only an intensity corresponding to that voltage. Okay. There is a question from Karanveer Bansal. Is it possible to explain question number 4 of week 3 assignment? Okay. I have to take out the question. Give me a minute. I'm sorry, I've not kept myself logged in the course page. So let me just log in. Can you type out the beginning of the question so that we are at the same page? Karanveer, can you type out the beginning of the question? Question 4 of week 3. So some of these questions are being solved by the teaching assistants. So please take a look at those videos. Assume that the gain coefficient is parabolic shape. Okay, let me just take out that. Just a minute. Okay. So the question is, assume that the gain coefficient of a semiconductor material has a parabolic shape. So this is assignment. Question 4, assignment 3, question 4. I hope the assignment 3 deadline is over, so I'm not giving away the answers. So G of lambda is given to be G naught 1 minus lambda naught by delta lambda G the whole square. So this is the shape, the gain coefficient. So we studied in class that the gain coefficient has a shape. We studied what is the reason for the lower cutoff and what is the reason for upper cutoff and so on. It's convenient to just assume it as a parabolic shape. So this is what it is. So when lambda equal to lambda naught, right? So this is G of lambda on the y-axis, and lambda equal to lambda naught, it is just lambda minus lambda naught the whole square. That becomes, this part becomes 0, so the peak value becomes G naught, and delta lambda G, you will see that when does this, so how do you understand this parabolic shape? So when does this G of lambda become, let's say, half, right? Half of its G naught. Let's say this becomes G naught by 2, which means this is G naught by 2 is G naught times 1 minus lambda 1, let's say, lambda prime, let's say, where it becomes half, minus lambda naught divided by delta lambda G, the whole square. You can solve this and you can find out what are those lambdas for which it becomes half. You will realize that delta lambda G in that sense is giving you a measure of the width of the parabola. Lambda naught is given to be 1550 nanometer, and this delta lambda G is given to be 15 nanometer. If you actually go ahead and solve this, you will get something like half equal to 1 minus lambda prime minus lambda naught the whole square divided by delta lambda G the whole square. So lambda prime minus lambda naught by delta lambda G is equal to 1 by root 2. So lambda prime is in fact plus minus 1 by root 2 because you're taking a square root. So you will get lambda prime is equal to lambda naught plus delta lambda G divided by root 2. And there is one more lambda prime, which is lambda naught minus delta lambda G divided by root 2. So in that sense, what I'm saying is that these are the lambda primes, right? At lambda G by root 2 wavelength away from the lambda naught, this G naught is becoming G naught by 2. So this width is simply twice delta lambda G divided by root 2. So this is actually root 2 delta lambda G. If your gain has the width corresponding to the lambda, the width of this gain spectrum for which the gain coefficient drops to half its peak value, right? So that's the meaning. That's how you understand this gain spectrum. Okay, let's get to the question. The length of the cavity is 400 micron. So I have a Fabry-Perot cavity, right, whose length is 400 micron. So in our notation, D is equal to 400 micron. Refractive index of the material is 3.6. Find the number of wavelengths that would satisfy the phase condition with G greater than or equal to 0.5 G naught. So I've already calculated G greater than 0.5 G naught. So this is the wavelength separation for which G is greater than half G naught. Now, under this, so the question is, in this range, in this gain range, or in this wavelength range, how many modes do you have which satisfy or which is falling within this wavelength range? because we just calculated G is greater than half G naught means, these wavelengths which are within this have a gain greater than half G naught, right? So how do you now calculate that? How many wavelengths are there? So if you, what is a phase condition? We know the phase condition for the modes of the laser, right? So the free spectral range for the Fabry-Perot cavity is C divided by 2n d. So this is 3. You can calculate what is the FSR, that is a spacing. FSR is simply the spacing. So if you remember correctly, this cavity decides the spacing between the FSR, which is the spacing between the frequency spacing between the longitudinal modes. The question we are asking is, you have a parabolic spectrum. Within that, you will have a large number of longitudinal modes. And in fact, this longitudinal modes extend all the way from 0 to infinity. Of course, they are all equally spaced. When I drew it, it is slightly unequally spaced. But what we are asking now is, if you put a line corresponding to G naught by 2, how many of these lines actually satisfy this condition? So we have to basically count from here to here. So the answer is now very simple. You have already calculated what is this width, what is this span, and you know what is the FSR. C by 2nd is, mind you, this is in frequency unit. So this is, FSR is in delta nu is in hertz. So corresponding to this, you have to calculate the delta lambda, which is the wavelength spacing between the modes. Now you're asking yourself the question, in a span of this root 2 delta lambda g, right? Delta lambda g is given to you. So that number is given to be, delta lambda g is actually going to be 15 nanometer. So root 2 into 15 nanometer is your span. Within that, how many, let's say this, so you have to calculate this delta lambda, that work you have to do. So within that, how many delta lambdas can be fit in? So it's a simple division of delta lambda g or root 2 delta lambda g divided by the delta lambda corresponding to the FSR of the cavity. Okay. So, I mean, why are we asking this kind of questions? We are asking these kind of questions because now it means that if I make a laser like this, and if the threshold is such that, all those modes above G naught by 2 are allowed to lace, this laser will have those many longitudinal modes. So the output of this laser, if you look like, it won't be a single line. It will be something like, it will be like this parabolic feature. This feature will remain, but then it will have so many longitudinal modes supported. This is how the output of a typical Fabry-Perot laser looks like. Now the question is, how do you know whether it is G greater than half G naught or whether G should be greater than 1/3 G naught and so on? That is decided by the inherent loss in the cavity. So depending on the loss, that's the threshold condition and so on that we worked out. So depending on that loss, all those modes which have a gain which is greater than or equal to loss is going to get supported in the system. So I hope that answers Karanveer's question. Vasundhara also has a question similar. Question 4 of week 3, calculate the number of longitudinal given this. So I think it's regarding the same question. I hope it's the same thing. Vasundhara has another question. Why with decreasing baud rate, noise variance increases? Oh, that's a very interesting thing, and that's a very important concept to understand. So to understand that, let's get into the laser phase noise. Before that, let me answer this question of Arjun, which is explain the generation of 4-PAM electrical signal which is required for 16 QAM. Oh, so in 16 QAM also the idea is the same. It's just that it's the same 4-PAM you're applying to get the 16 QAM. It's just that in 16 QAM, what you do is you have to apply it. Each of these 4 PAMs have to be applied to so here you apply 4 PAM. Here also you apply 4 PAM. And then you give a pi/2 phase shift to this 4 PAM. And that is what would give you 16 QAM. Right? So even here, you will, in each of these cases, you will pre-equalize your 4 PAM voltage levels so as to satisfy this nonlinear, or so as to undo this modulator nonlinearity that I was talking about. Okay, so I hope that is clear. Arjun, is that okay? There's no difference between 4 PAM and 16 QAM in that sense. In 16 QAM, you are feeding 2 4 PAM signals, and you are you have let's say in the constellation space you have this 4 PAM here, and you have the second set of 4 PAM signals, and that is pi/2 phase shifted. So that will be something like this, that is Q, and then a combination of this and this is going to give you 16 levels. So in that sense, the equalization is the same. There's one more question here from Pooja. How do we understand the saturation behavior of homogeneously and inhomogeneously broadened transition in a laser? So that's again a very interesting question. We have to do laser phase now, so we'll come back to that. But let's talk about homogeneous and inhomogeneous broadened laser system. Now, if you have 2 levels, right? Your ground state and your excited state, okay? And if your population, whenever you talk about these rate equations, right? So what exactly is saturation? I mean, if you understand it in a very general sense, saturation simply means that as you keep increasing your P signal input power, the gain will start dropping. And how do you understand this? It's actually very simple. If you go in with very few photons at the input, assume that there is enough population inversion in the system. If you go with very few photons, and let's say I'm talking about a gain of 10 times the gain, 10 dB gain. If I go in with a certain input number of photons, let's say I go in with, let's say, 10 photons. I'm just giving an example. I have enough inversion. Let's say I have inversion that corresponds to 10,000. I mean, I'm just giving numbers to understand the whole thing. I can very readily get 100 photons from the system corresponding to a gain of 10 because I have 10,000 carriers that are sitting in the excited state. Okay, so I get a gain 10. Now, let's say I increase the input signal power and I go to, let's say, 100 photons at the input, a level corresponding to 100 photons at the input. Now, that means that to maintain a gain of 10, I need to come out with 1,000 photons. So I need to have at least 1,000 ions or 1,000 electrons in the upper state. But I have already 10,000, so that's not a problem. So I'll get again a constant gain. My gain will be maintained as 10. Now further increase, let's say I go in with 1,000 photons, right? Or let's say I go in with 5,000 photons. Now, to maintain a gain of 5010, I need 50,000 photons at the output. But look, I don't have 50,000 ions at the higher upper state. I have only 10,000 ions at the upper state, which means your gain gets starting to fall. I can get only 10,000 divided by 5,000, which means I can get only a factor of 2 as a gain, which means this gain, which was 10, suddenly dropped to 2 when I came to a larger input power. So this is how one intuitively understands gain saturation, which means that any amplifier, whether it's an optical amplifier or an electronic amplifier, the gain is constant for smaller values of signal. At larger values of signal power, it starts saturating. Of course, in electronic amplifier, that has to do with the VCC voltage and so on. In a way, this is corresponding to the VCC voltage. This is like a reservoir which keeps giving you the ions that are required for the emission. Now, a homogeneously broadened system is where this phenomena happens. If I'm depleting a certain gain, so I said 10,000 ions or 10,000 electrons. Now, it's not that the 10,000 electrons are found in one atom, right? I mean, the entire volume of the system has these 10,000 carriers, extra carriers, which are ready to move from the conduction band to the valence band. So I cannot distinguish between one donor atom with respect to another donor atom. That's a homogeneously broadened system. I talk about all the ions. I cannot distinguish between the carriers or the gallium arsenide or indium gallium arsenide doped material in one location versus the other location. Now, there are these inhomogeneously broadened systems where instead of, so here, even though it's a band, it's a homogeneously broadened system. In an inhomogeneously broadened system, in the glass matrix, so typical example of an inhomogeneously broadened system is erbium in glass, which is what happens. You use in a erbium doped fiber amplifier, right? So you will have erbium in SiO4 silica matrix, right? And depending on the specific location in space, these rare earths are heavy ions. So there are these local electric fields that get produced, right? So, and these are actually doped in the amorphous glass, because by the time you make a fiber, the glass has become amorphous. It is no more kind of a crystalline structure, because you have kind of melted it and you have extruded it and so on in a fiber. So what really happens is the behavior of these extra ions in this erbium atom and this behavior of the extra ions in this erbium atom may be slightly different, which means that I can now think about energy states which are kind of discrete. You can talk about gain saturation between these levels. You can also talk about gain saturation between these levels, right? It's like saying that these set of ions and these set of ions may not talk to each other. You can saturate this set of ions which correspond to erbium, which are in a specific electric field matrix in glass, but that doesn't mean that these set of ions which are sitting in a slightly different energy state or which is slightly sitting in a different glass matrix environment, it doesn't mean that those get saturated, which means that the gain saturation for a given frequency, what does it mean for us? Gain saturation for a given frequency does not necessarily mean gain saturation for another frequency. Meaning, you see, you have a certain gain spectrum here. So let's say I have nu1 and nu2 going into my, entering my system. You saturate nu1 with 5,000 and you also go in with nu2. That nu2 is, so you saturate, so okay, let me just repeat this once again. Let's say now you have two frequencies, nu1 and nu2, going into the homogeneously broadened system. And let's say you are going in with 5,000 photons in our previous example. In nu2, you know that the gain of this, the gain experienced by nu2 is 2. And let's say you go in with 10 photons of nu1. What the system will now do is kind of distribute this 10,000 between the two, right? So you'll just see output divided by input. So it means that these 10 photons will not possibly get the small signal gain that is due to it. It will see the whole gain as a complete entity. So this 10 photons will also see a gain of only corresponding to 10,000 divided by 5,010. That's the gain seen by either nu1 or nu2. Okay, so even though nu1, this frequency, both these frequencies are amplified because there are energy levels corresponding to both these frequencies. But as far as the system is concerned, the ion sitting here and the ion sitting here, they are completely indistinguishable. Which means if you are saturating the system with two different frequencies, the system really does not know. It just shows the gain saturation behavior in total. Whereas in an inhomogeneously broadened system, let's say you could have here, let's say you have something like 10,000 ions here, and let's say another 10,000 ion corresponding to this or corresponding to this another energy state, right? You can completely saturate the red with going with 5,000 ions in nu1, but if you go in with 10 ions in this frequency nu2, which is in the green, you see there is a separate set of 10,000 ions that are available for green. So that will still see a gain of 10, whereas this guy will see, this frequency will see a gain of 2, which means the gain saturation actually happens independently. So that's the difference between the gain saturation of homogeneously broadened system and inhomogeneously broadened system. I hope that clarifies. Let's see, what's the next question? Please type in your questions if you have. There was a question on phase noise, which I missed earlier. So let's get to phase noise. Give me 1 minute. Okay, so let's get to the so we understand that the phase noise in the frequency domain is quantified through line width, right? Which is the width in the frequency domain. We also quantify the phase noise in the, this is frequency domain. We studied in the class that we can also quantify it in the time domain through what is called as phase error variance, right? And the sigma square of t tau is equal to phi at t plus tau minus phi of t variance of this. So just to clarify, your E of t, right? So E of t is the electric field that represents the output of a laser. Now that E of t is equal to, this is how we start, E naught of t e power j omega t is the center frequency of the laser plus phi of t. And what we are saying is that this phi of t is continuously changing with time. And what does this number represent? So let's say I plot my phi of t as a function of t, right? So initially I have a certain phi of t, then that phi of t changes to something else, it changes to something else, it just keeps drifting. Right? I'm just drawing it randomly right now. Now, what this means, this relation, means is that your sigma, this phase error variance, we said it is proportional to line width, which means that let's stop for a minute and see how we are trying to calculate the sigma phi square of tau. So you take phi of t at any time and then you calculate phi of t plus tau. So you say that I give a delay, I find out what is the phase after a certain time. So let's say take two instances where this is tau. I calculate what is the difference in phase, and that difference in phase, so which is this y-axis differences, and I take the variance of that. That's only one number. So if I were to get this as a variance, I need to do this as, I have to keep doing this process multiple times, which means I do this process. Then what I do, I take, I take the next time instant and then calculate, I keep this tau the same, right? I calculate what is phi of t plus tau minus phi of t. Then I take the third time instant, I calculate what is this difference and so on. Okay. Now, it simply means that so if this sigma square sigma square tau is related to the line width, it is also, so we also saw this plot sigma square tau. As you keep the way the laser phase noise works is, as a function of tau, if you plot this is a straight line, and the slope of this straight line is actually your 2 pi delta nu, where delta nu is your line width. So here I showed you a calculation for a specific tau. So what it simply means is that if I take a specific delay in my observation, and that specific, if that delay is a fixed constant tau 1, for instance, that is proportional to line width. But if I take a larger delay, what it means is that the phase error variance is actually larger. It would have drifted. So instead of doing this, suppose I had done this process where my first value is here, the second value is here. In fact, the way it will behave is not like this. It will actually keep drifting like this, which means if you take larger and larger tau values, the variance goes on increasing. That's what you're seeing in this plot. The variance goes on increasing, which means that this difference is actually going on increasing, which simply means that as you keep looking at larger delays, the phase drift becomes larger. Ideally, the laser is supposed to give you one phase, one single phase. Turns out that the laser is not doing that, right? The phase keeps drifting with time, and if you keep looking at farther instance of time, the drift in phase is really large. Okay, so that's about the phase noise of the laser. Now, what has it got to do with the baud rate? Now, let's take an example where I have a 10 gigabaud system. Okay, which means that my bit slot, let's just take a simple BPSK modulation. My bit slot where what I'm drawing is phase actually. Phase of t as a function of t. In BPSK, I'll do 0, pi, 0, pi, and so on, right? That's my BPSK modulation. Now, let's say the duration. Duration is what? 1 divided by 10 gigabaud, that's 1 by 10, 0.1 nanosecond. So that is 100 picoseconds. What is my demand from a BPSK modulation? Within this 10 picosecond, my phase should remain as 0. 0 with respect to some reference phase. Of course, there's no definition for absolute phase. It's all with respect to something, right? So essentially, we are saying that if this is with respect to the reference, I call this as 0. I need this part of my time to maintain a phase shift of pi. So let's say I have 0 phase, and then I have pi phase. Let's say at this point, the phase changed. Now, what my demand is that during this interval of time, where I have modulated it to be specifically 0 phase, I don't want the laser to misbehave and say that, okay, the laser, because of the phase noise of the laser, it should not change just because of the phase noise of the laser. It should not change from here, for instance, it should not change phase because of the phase noise of the laser. Because if that happens, then my phase modulation is going to be utterly useless because the laser is changing its phase on its own. It's not listening to the modulating signal, right? That's not something that I want. So what is the connection to baud rate? So it's like this, the symbol duration is now acting like this tau. If my symbol duration becomes longer and longer, instead of 1 gigabaud, let's say I'm doing 1 megabaud modulation, right? Now 1 megabaud would correspond to 1 microsecond duration. If the phase at this point and the phase at this instant of time, if they had changed by a large amount, and in case of BPSK, my tolerance is pi. I should not allow it to change by pi. Forget about pi. I should not even allow it to change by, I can put a margin and say I should not allow it to change by even pi by 10, right? So if this allows, if this changes by pi by 10, for instance, because of its own phase noise, then this is not a good laser. So in other words, for a given laser, for very fast bit slots, let's take 100 gigabaud system, right? So that is 0.01 nanoseconds, which is 10 picoseconds. Every 10 picoseconds, my symbol is changing. So which means I need to maintain that phase integrity only for 10 picosecond duration, which means it's like saying my tau is only very small. And within that, if I don't allow the phase to change by a large amount, I can still do it. Which is so that's the reason why the phase error variance or the noise has this dependence on baud rate. Any other questions? You need to type in the chat window. I must say that the transcripts, the notes are not really up to the speed as you wish. We are working very hard on that. You see, these video files are sent to some automated software, and the transcripts are first generated, the SRT files are first generated, and then we are working on converting that to text. It should work faster, so hopefully we will be able to catch up with the material and provide you the exact transcript very soon. We are working really hard on that. Any other question? If not, we will stop the session here. And thank you for your nice questions, and keep watching these videos. Things are a little harder than what it was before, but if you were to get to the heart of coherent communication, I think these are some very basic constants, basic concepts which need to get ingrained in our minds to be able to design this. Okay, there's a question from Rajshekhar Reddy. Which of the following has the highest spectral efficiency at Nyquist sampling rate? 16 QAM at 10 gigabaud, 16 QAM at 20 gigabaud, 16 QAM at 16 gigabaud, 16 QAM at 40 gigabaud. Oh, sorry, Vaidya Devi had also a question earlier. Okay, so going back to Rajshekhar's question, highest spectral efficiency at the Nyquist sampling. So Nyquist sampling already defines what is a sampling for a given baud rate. Okay, so I'm not going to give away an answer. I would give you the tips how to solve it. You please solve it and put it back in the forum, and we will discuss. Because if I give away an answer, then you will just accept it. So you know that if it is a Nyquist sampling, you know that bandwidth, twice the sampling frequency is what you would look at. Now let's take, I'll probably do it for one case. 16 QAM at 10 gigabaud, right? So this is my carrier frequency. You have to tell me at what kind of pulse shaping is this? Do you mean Nyquist sampling or Nyquist pulse shaping? Both are different. So let me show you for both. So let's take non-return to zero, NRZ. Okay, that's the pulse shape, which means that in my 16 QAM, I'm maintaining this condition that 1 remains 1 until the next 0 occurs. So I'm not doing any shaping in the time domain. Okay. So this is the carrier frequency, and if it is non-return to 0 and this is 10 gigabaud, it means that this is how the spectrum is going to look like. This is omega C. This is omega C plus 10 gigahertz. The first null appears at omega C minus 10 gigahertz, which means that you are occupying 20 gigahertz if it is non-return to 0. But if you do what is called as Nyquist pulse shaping, what you can potentially achieve is, this is frequency domain, okay? You can pack this spectrum. Forget about these side lobes, but then you can pack it within 10 gigahertz. So in case of 16 QAM NRZ with 10 gigabaud, your occupied bandwidth is 20 gigahertz and your bit rate, it's not polarization multiplexed, so it is just 10 gigabaud multiplied by 4 bits per symbol. So this is 4 because it is 16 QAM. Two bits per second per hertz. Now, if the same thing is with 16 QAM Nyquist shaped 10 gigabaud, the spectral efficiency simply becomes 40 Gbps divided by 10 gigahertz, because with Nyquist shaping, I did something in the time domain so that in the spectrum, my occupied bandwidth shrinks. And you can't shrink a spectrum smaller than this. So this would be 4 bits per second per hertz. Now you can work out for other formats. So Vaidya has a question, assignment 3, question 16. Let's see. Assignment 3, question 16. Was there a question 16 in assignment 3? Can you start typing the question? Oh yeah, I see the question. Okay, the question is find the shift in the wavelength when the operating current of the laser changes from 50 milliamps to 100 milliamps. Vaidya, is that the question that you wanted me to answer? Can you respond in the chat window? I will start answering after you get after I get your response. Okay, in any case, let me give you a hint. So this is regarding the chirp of the laser. I'm not going to completely solve. I think these assignment solutions are put up in detail, so you can take a look. So the line width enhancement factor, so this is assignment. Alpha is given to be 5, and the adiabatic chirp coefficient, which we were calling as kappa, is given to be 20 terahertz per watt. Yeah, so this is the question you want. Okay, so what does it mean? I have my light intensity versus current. This is my threshold curve. The question is, when the operating current changes from 50 milliamps to 100 milliamps, you have a change in power, right? But in addition to that, there is a change in center wavelength. That's what we learned in the class. In the videos, we learned why the center wavelength is shifting as you change the current, because as you change the current, the carrier density changes. Carrier density changes, the refractive index changes. And the refractive index changes, the wavelengths that are supported by the Fabry-Pérot cavity changes, and that's how you will start getting a chirp. And so the question is, so you know that it is changing from 50 to 100 milliamps. So I know that the change, this is okay. The assumption you're making is it's above threshold. Okay. Okay, so this is a straight line now. So if I call this as power instead of light, this is power. So because it's a straight line, I know that dP by di, this in the region that I'm assuming it's a straight line. This is the same as let's say P divided by I. So my dP is what would be dP now? This would be di times P divided by I, and the current changed by 50 milliamps multiplied by power divided by let's take the reference at 50 milliamps. So I get the value of power. So the power at 50 milliamps is 0.5 milliwatt. It means that my dP is 0.5 milliwatt because you will now you can find out, the slope efficiency is given, so you can find out what is dP. You can find out what is the frequency corresponding to the first current, because you know that the adiabatic chirp is alpha by 4 pi times kappa times power at this bias 1. You know what is the frequency, you can find out what is the frequency corresponding to this because you know the power and the current at those values. So now you can find out the difference in frequencies. That will be the frequency shift, and from that you can calculate the wavelength shift. I hope that answers your question. Is there any question? Any other question? Okay, so if there are no more questions, we will close the session now, and I'll meet you again next Friday. Very strongly encourage you to go through the videos of up to lecture 5, week 5, before you come on Friday, so that you can ask all kinds of questions to me. Thank you. Stay safe.